happy to introduce the next speaker, Motiejus Valiunas, speaking about free-by-cyclic groups, equational, Noetherianity, and growth rates.
Thank you very much, and thank you for the organizers. So, yeah, I guess I'll be referring to some of the things that were introduced last week. So last week we saw already things, well, free-by-cyclic groups. We saw it in the first talk of the conference. We saw cylindrically hyperbolic groups in Stephanie's talk. So there are lots of people who are not here anymore and who are introduced things that I will be using, but I guess I should introduce them as well. But there's one thing that's not been talked about yet, so it's equational Noetherian groups. So I guess I should start introducing that. There was supposed to be a talk on that on Friday, but it's not. The speaker didn't come, so we'll get some sort of knockoff talk on equational Noetherian groups. All right. So the idea is to consider equations of the groups. So we suppose we have a free group of finite rank, and we look at elements of the free group as equations in a given group G. So we view an element, so let's say free group with bases x1 up to xn, and we look at an element of a free group, which is just some word in elements x1 up to xn, as an equation in a group G, and by that I mean that given n elements in the group G, we set an element as G1 up to Gn, where S is that element, that word, just to be the image of S under the homomorphism, where this phi is a homomorphism sending from free group to G, sending basis elements to the G's. So that's a thing we can do. And then we can consider solution sets of equations. So this original, the motivation, well, if you ask different people, you get different motivations. But the sort of Russian school who I feel like introduced it first, they thought about extending algebraic geometry, concepts of algebraic geometry to groups. So in this setting, we can think about some sort of varieties in a group. And so given a system of equations, and the system of equations is just a subset of a free group, Fn, and the group G, we set the variety corresponding to that subsystem is just the n tuples of elements such that all the equations in the system evaluated at this tuple is 1 in the group G.
Well, in your notation before, it's an equation, so you have to have 1 somewhere, right? Equal something.
Sure,
Otherwise
yes.
what map? Just
Yes, it's
it's a what map or which you define?
sure.
Said the word.
I understand, but formally it's not correct.
Yeah,
Okay, you want
it's not correct in English, but it's not some. Yeah, it basically just introduced a notation. Okay. Yeah, we can. Okay.
It's like a relator versus a relation.
Let's say word map. Okay, but the idea is I want to consider, well, this is an equation, and then we're going to consider the systems of things like that. So then what's an equational Noetherian group? Well, equational Noetherian group is a group where every system of equations is equivalent to a finite subsystem. So given such an S, I can find a finite subset of this S that has the same solution set, the same variety. So a group G is equational Noetherian. If, well, for all ranks of the free groups, so for all n at least 1, and for all systems of equations, so okay, for all collections of elements in a free group, we think of, there exists some finite subsystem, finite subcollection, such that the variety of S naught is the same as variety of S. Okay, so that's something we can think about. So I guess since this is less standard, I should give maybe some examples, some non-examples to say, well, what sort of things we can expect, and what sort of maybe abstractions we have that not all groups satisfy its property. So they come basically in two types. There are easy algebraic examples, and then there are hard geometric examples. So easy algebraic examples, these are basically more or less observations. Some of them.
Isn't it a little restrictive to ask for this zero to be completely S? I mean, you could have two polynomial equations and you need the third one that's not in the list, but that represents all the solutions. That typically happens.
So, okay, maybe someone in the audience will correct me, but I think it's still open if your formulation is equivalent to this one. So if you can get a finite subset of the free group, that's not necessarily a subset here that has the same solutions. So I think that's still open.
Could you please repeat the question? I didn't follow.
So basically, if you define this S naught to be a subset of S, can you take S naught to be just a subset of a free group, a finite subset of a free group?
The question is, if you have a finite subset of the free group, whether what is true?
That the same thing.
Could you please repeat the same thing?
It's so there's a question. Okay.
If you have x squared equal 1 and x cubed equal 1, so the solution is divided by x equal 1, which is not in the list.
Yes.
Finite.
So the question is, can you just say this as not a subset of free group, and all the same condition holds? So this is somehow a weaker property a priori, but I think there are no examples to show that. these are different. Yeah. So, but I guess the standard definition is just to take a smaller subset of S. Okay, so for some easy algebraic examples, we can think about things like linear groups. And this is basically just a Hilbert's basis theorem, which yes, allows us to think about these things. And then there are some small sort of algebraic subsets. So abelian groups, you can generalize them to metabelian. You can generalize those to abelian binomial-potent. Or abelian bipolar-cyclic as well.
Мясников-Карлан function is also who for the Мясникov-Kарлan function?
So which one, abelian binomial-potent? No, this is all the result of Bryant in the 70s. Yeah, this came before even the whole study was introduced of equational theorem groups. Well, and there are some closure properties what they pass to. So let's say Ian passes to direct products. Here I just mean direct product of two factors, or finitely many factors, subgroups, and finite extensions. So all of these results are not too hard. Some are more or less trivial. Some require a couple of pages proof, but they don't really require much else and much theory developed. So in this,
All linear groups are equational.
Think so, but this is not in the easy examples category. Okay, so maybe some non-examples.
For linear groups, it is the mutual property.
Yes, for linear groups is basically the statement that the polynomial ring over, and with this formulation it's enough to say polynomial ring over Z with integer coefficients is Noetherian. That follows directly from that. Okay, so non-examples, we could have some Bumps accelerators, so non-Hopfian finitely generated groups. For instance, the favorite one of everyone, PS23. Then, what else do I have? Yeah, I have some Reef products. For instance, S3 reads Z. So this metabelian case cannot be extended to, let's say, three-step soluble case.
But isn't it a linear group? Which group acts for you when you write Reef products? It's Z that acts or S3 that acts?
Yes, that.
Z that acts. And S3 is just permutation group or?
Yes. You can take any non-abelian group.
But this one is linear, right? You just mentioned all linear equation and theorem.
Is it linear?
Well, the order of finite subgroups is not bounded.
But S3 is a finite group, or?
Yes, well, it could be, but Henry disagrees that it's linear.
It's not linear, it's finitely generated and residually finite.
Ah, yes.
Yes, for instance, that's an argument for that. Yeah. Then we could take some more wacky examples like the direct sum of all finite groups. Which is also something. Okay, but then there are some also examples which require quite a lot of work. So the first, there was the paper of Baumschlag-Mieslikov and Rezlenikov in a series of papers of algebraic geometry over groups where they talk about these things and they ask some things. So for instance, are hyperbolic groups equational theorem? Does it pass to free products? So if you have two equational theorem groups, it's a free product of these groups, equational theorem. And these sound like they're simple questions, but they don't, well, they're not known to have simple answers, but they do have answers that came maybe 10 to 20 years later. So yeah, so these are hyperbolic groups. So Gromov hyperbolic groups are equational theorem. So the torsion-free case is due to Sella. And then the general case due to Reinfeldt Weidmann. Okay, this 19 is actually a 15. Okay, so in this direction, like one of the more general results is that this passes through to relative hyperbolicity. So this answers this question, for instance, on free products. So hyperbolic relative to equational theorem groups. This is a result of Groves and Hull. Also in 19, but this 19 is a 17, not a 15. Okay, I guess I could mention one of the more recent ones are fundamental groups of three manifolds, and three manifold. So this is a follow-up of this work as Groves, Hull, Young, published this year. Okay. So, somewhat in a similar flavor as the free manifold result is the result that I want to talk about. So this is our result. It says that all free-by-cyclic groups. So free-by-cyclic, and by that I mean groups. By that I mean that the free kernel is finitely generated. So we have a Fn semi-direct Z, where n is less than infinity. These are equational theorem.
There's a recent result on Mark Newton says any finite generated infinite rank by Z groups and doesn't finite rank free by Z groups. So I think then you can
Yeah, embeds actually. Okay. So I know another result that sort of follows from the literature, but it's not stated anywhere, is that if you take if you move the brackets around, so if you take a free-by-cyclic group that's finitely generated, but the free kernel is not necessarily finitely generated, then it's hyperbolic relative to finitely generated free-by-cyclic groups. So then it could be combined with a relative hyperbolistic result. Just stated as well for those.
Sorry, can you repeat what was Martin-Newton?
It proved that any finite generate free-by-cyclic group can be embedded into a finite rank free-by-cyclic.
Embedded.
Okay, that's interesting. So I guess we don't need. We can sort of generalize this by not requiring Fn to be a finite rank, just to say the whole group is finite generated. If the whole group is not finite generated, then that fails. But if it is, then. Okay. So I guess the main application or the main motivation of our work is what Koji Fujiwara, I guess, would have talked here if he was here. So these are growth rates. So it was briefly introduced by Carl Frederick last week, so I'll just reintroduce it quickly as well. So if we have a group generated by a finite set, then we can think of the exponential, exponential in quotes growth rate, because it might be sub-exponential, which is just the limit, if you take the ball in a kilograph of, let's say, GA. So you take a ball in a kilograph of radius L, you take an nth root of that, and you take a limit of these things. So this is some number. This limit exists. It's a number between 1 and infinity. And let's say G infinite. Just for safety. Okay, and then we can think about what happens if we change the generating set. So we look at another generating set, another growth rate. So we set psi of G to be just the set of all numbers like this. So it's the EGA, which G is generated by A, and A is finite. Okay, so that's a subset of this 1 infinity. And I guess we can ask, well, what properties it satisfies? So I guess I should mention that this might be badly behaved for some groups. So there's a group first constructed by Wilson, which have exponential growth but not uniform exponential growth. So in this terminology, in this notation, there exists G such that EGA is bigger than 1 for all or for any a, it's the same thing, but infimum of the psi of g is 1. So there could be badly behaved things. There could be, it's known that this doesn't happen for many nice classes of groups. So for many nice classes of groups, if you have exponential growth, then you have a lower bound on this exponential growth. But there's the much stronger result. Just theorem, Fujiwara. Which states that we have a hyperbolic metric space and we have an action of g on x which is acylindrical, and non-elementary. I guess I don't need to say that, but just for the sake of sanity, I will. So the result says that if the group G is equational Noetherian, then psi of G, plus a condition, which I'm not going to talk about, then psi of G is well ordered. The condition is satisfied automatically when x is a tree. So I'll talk about mostly about actions on trees. So I won't say this. But as a corollary of this, is an earlier result of Fujiwara and Sala in 23, which says that if G is hyperbolic, then psi of G is well ordered. And before this result, this basically the well ordering wasn't known for basically any group. So it was at this point it was new for free groups. That this result holds. So it's really some sort of strong non-trivial thing. But yeah. So that's that result, and then the corollary of our theorem. Is that if G is free-by-cyclic, then psi of G is well ordered. All right. So I guess in the remaining 20 minutes, I would like to say something about the proof. Okay, so the proof uses a couple of tools. The first is a cylindrical hyperbolicity. So it was already mentioned in the Fujiwara's result that you need an action to be cylindrical. Since I'm mostly going to talk about actions on trees, I'll only introduce cylindrical actions on trees because it's easier to write down. So if x is a tree, and let's say G is torsion free, which, okay, I only consider actions of torsion free groups, so that's okay. Then we say that, okay, so this is first tool is a cylindrical hyperbolicity tool. We say that G, the action of G on X is K cylindrical if intervals, so let's say paths of length more than K have trivial stabilizers. So the action might not be proper, but if you take 2 points that are far away from each other, then nothing stabilizes both of these points. Yeah, and then we say that so K cylindrical is this, and a cylindrical if it's K cylindrical for some K, and I guess I should say non-elementary if, how do I say this? There are no fixed points and G is not virtually cyclic. So yeah, so this is one of the things we'll use using, I guess. Yeah, that time I explained why free-by-cyclic groups are acylindrical hyperbolic in almost all cases. So they have these actions on non-elementary cylindrical actions on trees or something else in some other cases. Okay. The second tool, and this is the main tool that helped to prove the relative hyperbolicity result. It was also building on earlier things developed by Sala, so related to the earlier hyperbolic result. So really, all the sort of geometric results come from this sort of framework, and these are non-divergent sequences of homomorphisms. So this is a Lagrove's hull. The way they introduced. So for that, I guess I want to say slightly different, take a slightly different viewpoint of what it means to be equational Noetherian. So in here, we start by fixing a non-principal ultrafilter. If you don't know what it is, don't worry. It's basically just something that allows us to ask the subsequences to make things work and converge. But if you don't like ultrafilters, you can think about subsequences. So this is on natural numbers. And we consider sequences of homomorphisms from a fixed free group of rank n to a group G. Right. So we have some sequence of homomorphisms, and that allows us to define the omega kernel of the sequence. Phi, these are just elements in a free group that omega almost shortless, so for in a big set of natural numbers with respect to omega, are sent to the identity by these homomorphisms. So I'll just say phi I of G is 1 omega almost surely. It basically means that there's like a consistent way of pass to subsequences such that there is some subsequence where this happens eventually, let's say that. Not really, but there. Okay, so that's some, I guess, if you know what an ultrafilter is, you can show it's a normal subgroup of the free group. And then the definition / theorem, but not very hard, to show this is that the group G is equational Noetherian, but only if for all sequences of homomorphisms phi I as above, we have this omega kernel contained in the actual kernels of homomorphisms omega almost surely. So there is some sort of changing of quantifiers happening there. Yeah, so I guess it's an exercise if you're bored to show that these definitions are equivalent. Okay, so how does this help? Well, now suppose we have a group that is asymmetrically hyperbolic, so it acts asymmetrically on a hyperbolic space. Then what this main technical result of Gross and Hull says is that you don't need to consider all sequences of homomorphisms, you just need to consider non-divergent sequences. And divergent is defined the following way. So, so suppose we have group acting on X, the action is acylindrical and non-elementary, X is hyperbolic. So we have a single action on a hyperbolic space, and then the sequence of homomorphisms is non-divergent. I guess I should say with respect to this action, with respect to this action, what we do take, we take an element in a free, so let's say X, we take its image, we take a basis element on a free group, so we take phi of S, where S is a basis element in in the free group, and we look at this image of this point. We look at how far away they are, so the distance between these 2 points. We want to first maximize this. Then we want to take the point which makes this optimal, to take point x, which makes this an infimum, and take the ultra limit. So it's non-divergent if this whole thing, which is a real number, or infinity, is a real number.
So you said S now is finite generating set of F.
Yes, where
It was a set of equations you should.
Quit F.
okay, let's do B as a basis
It's independent.
of Fn. I guess technically it is a subset of a regroup, so notation is still sort of consistent. Right, and then the theorem of Groves and Hall says that instead of considering all sequences of homomorphisms and checking that condition, it's enough to check that condition. I guess I should denote that condition with something. So we have this condition, which I denote by star, and then the Groves and Hall result says that it's enough to check that for non-divergent sequence of homomorphisms. So G is En if and only if star holds for non-divergent phi. So it's a bit of technical condition. What it really boils down to when you have a group acting on a tree, let's say group acting co-compactly on a tree, you can just pick your favorite vertices, which are orbit representatives of that action in the tree, and then consider only the actions where the basis elements are just sent to those stabilizers of those vertices. Possibly some stable letters in the graph groups as well. But it basically allows you to have some control so that if you have a group acting on a tree where the vertex stabilizers are somehow simpler, so either you understand them or you can use some inductive arguments and pretend you understand them, then this sort of resolves. Okay, so I have 6 minutes, so I should probably say what sort of splittings I have. So maybe I'll introduce the results first, and then if I have time, I'll define what I mean by them. So we have various actions on free-by-cyclic groups, various splittings of free-by-cyclic groups. For F, let's do big N if it's the kernel. And it basically depends. So these groups are defined by how the generator Z acts here. So we have some automorphism here, let's say psi. It only depends on the automorphism, so we can think about automorphisms. And then automorphisms can have various growth not in this sense, growth in a specific real cyclic group sense. But in particular, it can be polynomial of a given degree or exponential, which I probably won't have time to define. But what we do have is a couple of theorems. So the first one allows us to reduce from the exponential growth case to polynomial growth case, which sounds like polynomial growth is easier, but sounds only, I guess. So this is a result of Damaini and independently by Ghosh. Which says that if, let's say, okay, let's do small psi, let's do just automorphisms of a fan. So this small psi has exponential growth then free-by-cyclic group defined by that automorphisms is hyperbolic relative to the ones where this has polynomial growth. So Fni semi-direct psi I z where psi I in alt of Fni has polynomial growth. Okay, so we can reduce to a simpler case. And then for polynomial growth case, so that result then follows directly from the reduction to the polynomial growth case follows directly from the relative hyperbolicity stuff. In the polynomial growth case, we need to do a bit more work, and we use two other splittings, depending on if the growth is okay. If the growth is constant, which means the automorphism is has finite order, then that also follows easily because we know this all passes to finite extensions, so we can just take a finite extension, take a finite index subgroup of our group, which is free time cyclic, Fn times z. For Fn times z, this is easy. You can use whatever you want. It's linear and stuff like that. Okay, which is, by the way, the before, like 15, a bit more than 15 years ago, this was the only way we knew how to show that free groups are equation of Noetherian is to show that they're linear. So it's really some sort of, the roots of this concept are very algebraic. Okay, so we have then two other splittings. One that allows us to, if we have something of polynomial growth, polynomial degree growth, it allows us to reduce the degree of the polynomial. So this is theorem Neo-Mandrew, Motiejus and Monika Godlinska. which says that if psi is, okay, I'll say another thing, UPG. If you know what UPG is, great. If not, I don't have time. UPG, so basically it's, okay, you can pass to find it in a subgroup to assume that psi is UPG, so you don't care about this. Of polynomial growth of degree d, which is at least 2, then there exists a splitting of Fn by z with as stabilizers infinite cyclic and vertex stabilizers free-by-cyclic but of lower degree polynomial growth. So if an I semi-direct psi I z where psi I has polynomial growth of degree less than d. And another theorem by Andrew and Martino, just 2 people. 20-something, which says that we can do similar thing on for, okay, let's say same for d equals 1, but in that case, edges are z squared instead of z. And they have some other nice properties which you can deduce, which you can, yes, check in these splittings. Okay, so these splittings are cylindrical, which is what one of the things that we need. And then there are some nice properties which allow us to pass, to show the result for linear growth and use this to deduce polynomial growth, use that to deduce exponential growth. Okay, I'm out of time. Thank you.
Do you have questions? Yeah.
Do you have an example of free-by-cyclic group that's not linear?
Do I have an example?
Or somebody has
I don't know, someone in the audience? I feel like
it's an open problem. There is some candidate. Gerson has a non-candidate group which people do not know that one is linear. So there's some candidate people think might be not linear, but
okay, there's some candidate.
Forgive me if you said this and I missed it, but what's the status of equational Noetherianity for the class of acylindrically hyperbolic groups? Are the counterexamples? Is it open?
well, it passes to subgroups. So if you take like any group you want and then take a free product with that, let's say, then that's acylindrically hyperbolic. So I mean, yeah. So you need some sort of class that is closed under subgroups if you want to have that. And in that, well, the relative hyperbolicity result is, I guess, one of the more general ones.
If you have free-by-cyclic groups, is there any chance, at least conjecturally, to guess what constant could be growth rates of such groups?
So there are some early papers where they give, well, I mean, so it depends on the generating set. I mean, what we can think about, for instance,
But I think not saying what is genetic set. I just give you some constant, some number, and ask, is this constant is the growth rate of some free-by-cyclic group?
Right. No, that I don't know. I think that sounds like very. Somehow the way you show that this is well ordered is just to say you have a sequence that is decreasing, and then the limit of that sequence is also growth rate. But somehow it's not very explicit in what actual growth rates we can get this way.
So going back to this question about linear groups, but you need only to know, even if there are some candidates, you need only to know for polynomial for this class.
Yes.
Maybe this class is linear.
But isn't Gerson's group also polynomial?
It is polynomial? The candidate is polynomial? Okay.
Yeah, it's. Yeah. Sure, I mean, it would follow, yeah. If we can show they're linear, then yeah, you just need to show that the actions are cylindrical to deduce the growth rate result, basically. Don't know whether they're linear.
Do you know if Gerson's group is contained out of 3?
Sorry?
Gerson's
Well,
group
this is so, like, it's also not known whether out of 3 is linear, right? And I can't remember whether.
contained out of 3. No.
Okay, so no more questions. Thank you. Let's